Hi everyone, today we're going to be talking about transforms in linear algebra and what they do and how you want to think about these. So, if we recall from algebra, there were these things called functions. Let's call a function a transform just to kind of understand. They're kind of synonymous with each other. In algebra, we learned functions. Here, we're going to just apply that ideology to functions. And it said that for if we had a function f and we put in some value of a in the domain, we get out some value b in the codomain. And specifically, all possible values that the domain can map to is called the the range. We're going to get a little more technical with our math now that we're in linear algebra, right? You're probably taking this past Calc 2, Calc 3. You're just bordering on differential equations linear algebra. Mapping the functions that we're talking about, we need to get a little more practical with them, is my point. But what we're doing here is we're mapping a to b from a domain. There's also a space called a codomain, and all functions that the domain can reach is called the range of the function. Okay, so hopefully pretty easy, but in linear algebra, it's going to get a little different. Now, we'll keep the idea of the domain, the codomain, the range, the idea of mapping one value to another, but in this case, we're going to be transforming vectors, right, or linear systems themselves. So you can think that in V1, we could map it to V2 and get a whole new vector out, all right? So that's how I want to think about it, but let's get into actually deriving the transform. So imagine we have some vector space V which contains the set of functions, or in this case vectors. So let's say V1, V2, V3 dot 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 Vn. And let's say that we're going to map this space to W. So if we look at W, this is a set of vectors W1, W2, dot, 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 Wn, okay? So what our goal is going to be, how can we express this set of vectors as these ones, okay? That's the grand story of things, or the grand idea. So, like, for example, if I have some vector like this in R3, okay, and let's say this is right here is a plane, specifically, this would be the YZ plane. This is the YZ plane. How could we maybe reflect about this, okay? That's what we're trying to do with transforms, and where they're derived from is that W. So W1 is some scalar multiple of our first vector. And in this case, let's break it down into its components. So expand this out. So any V sub at symbol, I guess we'll call it, can be comprised of x1, x2, x3, dot, 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 xn. Okay, so we're going to break the vectors down into its components, so when you see it, just don't be confused why we're doing that. But anywho, x1, and I'll actually make this a little different. I'm just going to assume that you guys kind of know some linear algebra at this point. To a good degree. So we're just going to go for it. Row, I always forget, it's row column times x. Geez, I need to learn how to draw, guys. Dot, 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 A1n xn, okay? W2 then follows a row 2, column 1, x1. I'll just go dot, 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 A 2nxn, okay, and then dot 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 wn is equal to a row m, column 1, x1, and I'll just even draw this out too, a m2 x2 dot 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 AMN XN. So hopefully that's not just a bunch of word salad to you. I'm very sorry if it is, but this is just a linear system. W1, vectors W1 through Wn can be expressed as linear combinations of the components of corresponding vectors from up here. Okay? So let's put this in a different form. Let's say that the W vector, W1, W2, dot, 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 Wn, right? So any vector in W space, we'll call it, can be expressed as any vector in V space. Okay, and specifically, this will follow the matrix A11, A12, dot, 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 A1n, dot, 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 AMN, dot, 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 AM1, dot, 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 dot. Okay, so hopefully you can see the system here. I really don't feel like drawing that all out. Let's just pull out all the x values, x1, x2, dot, 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 xn. Okay. So this is our linear system. In this matrix here, okay, this guy, we give a special name, and he is called the matrix, sorry, the standard matrix. Geez, I have my textbook here in case I get lost with some of the stuff I'm trying to show, but this is the standard matrix. I always forget the name of this guy. Not to be confused with standard basis vectors, literally just, although they do come in handy, standard matrix. Geez, I don't know why that was so hard for me. Standard matrix, smiley face. I did that so well. So yeah, this guy is what this basically says is any vector in W space can be expressed as a scaled version of this X vector that's going to transform it in some way. And this array of A's is a transform. So let's give an example of one. The book that I have here gives too complex of an example, so I'll just pull one out. Let's say we're in R2. Simple XY, okay? And let's say we have some vector that points here. V1, and let's say that V1 has components to it. Let's say this is E1 and this is E2, and together they hit this point, they go to this point of 1, 1. Okay, how might I be able to go about flipping it like this? Okay, and then we'll call this one V2, okay? Notice what changed. Okay, if we break it down in its components, this is negative E2. Or sorry, E2. Just E2. Jesus. E2. And this here is E1, but it's negative. Okay? So we just flipped E1. So this would be a reflection about the y-axis. Right? So about the y. Right here. So basically we took this guy and we flipped him right over. So he comes to the coordinate of negative 1, 1 in this case. Okay? So let's call V2, and we give the standard matrix, I should point out, we give it a special little symbol. Well, you'll see it two ways. Okay? Standard matrix could be T of A. T of A in A being anything that you're evaluating for the transform. You also see TA like this, and then maybe something in here. But the general matrix is given this notation. Okay? Alright, so we need to describe V2 as some TA T sub A of V1. Okay, and TA is going to be a matrix, like we showed up here, that is some form of scaled version of X that will give us W, which in this case we'll scale V1 to give us V2. Okay, maybe you can just see it, but let's show the theorem. So the theorem says, the theorem states if I want to find T of A overall, then plug in the column vectors that give you the image. This is called an image. So that your transform will output this thing called an image, which is the vector you get. So we give this guy a special name, very important, image. And to do this, with respect to your standard basis vectors here, put in your transformed image. So what this TA of E is saying is, when we transformed this vector, what did we get out? Okay, and make that into a column vector. That's all that's saying. And then same with this here, T of A, but for E2. Okay, and if you have, for all components, or if you're in R4, you do 4. If you're in R5, you do 5. If you're in R3, you do 3. You do the number of columns as you need, and they're all going to be the transform of your individual vector components. So if you have a Y component, okay, does it change? No, it doesn't. So you're just going to plug in whatever you have. So in this case, our standard basis vectors follows that, okay, well, the transform of this E1 went negative, so E1, the TA of E1, is equal to negative 1, 0, right? Because that's the vector we got out. That's the image we got. So we put in as a column vector. We transpose the vector. That's going to be sitting as a row vector, and we flip it to a column-like vector. And then we're going to augment this with E2, which if we look, it did not change and will stay as, and if I go down, TA of E2, 0, 1. So it didn't change, so we're just going to put 0, 1. And in fact, when you multiply V1 with this T of A, you're going to get out V2, and I can prove that. So V1 was 1, 1. So let me just do it like this. You have to make sure the multiplication works. Negative 1, 1, 0, 0. So let's check. Does the multiplication work here? So vector, this is T of A. We're going to output V2. Notice this is 2 by 2. This is 2 by 1, right? These equal the dimension or the size of our output vector will be 2 by 1, which is a vector, right? Same dimension vector as V1 is. But notice when we do the multiplication, we're going to multiply these. This is going to give us negative 1, and then we go to the lower one, and we're going to see just 1 here. So you get out negative 1, 1, which is exactly V2 here. So hopefully that helps you to kind of visualize. I know that was a little messy, but hopefully it lets you visualize transforms. There's a lot of transforms to go over. I might make a video on it, I don't know. But they're not hard to derive. All you need to do to derive any transformation is just imagine what the basis vectors are doing as you flip them. Do you want a reflection across the xy plane? Well, change the z, right? Because the z will change from positive to negative or negative to positive, right? It's just going to flip across the plane. That's how you develop these with this simple tool that you can use. So, all right, guys, have a good one. Bye-bye.